All right, hello and welcome back. So this is another ALEKS topic that's called solving applied dilution problems. This is definitely a little bit more of a challenging problem-solving type topic. The actual calculations are, again, pretty straightforward, but the actual, understanding of the concepts behind that's going on here is definitely challenging, I would say. So I'm going to do two different instances of this topic. Not sure if I said that already, but let's go ahead and jump into it. So basically, let's start by just reading the words, and then I'll explain my pictures here. So it says a geochemist measures the concentration of salt dissolved in Lake Parsons. That's over here. We got a very high concentration, 33.8 grams per liter. The geochemist also measures the concentration of salt in nearby lakes, 4.76 grams per liter. So this non-isolated lakes versus Lake Parsons, this isolated lake, means that it's not connected to the other lakes. It's sort of its own independent thing. Assuming the salt concentration in Lake Parsons before it became isolated was equal to the average salt concentration in nearby non-isolated lakes, calculate the percentage of Lake Parsons which has evaporated since it became isolated. So essentially what they're saying is that this is going to be like a dotted, similar volume. At one point, Lake Parsons was this full, and then a bunch of the liquid evaporated. And so then, this evaporated, our liquid level went down, and then the salt concentration was just sort of concentrated down here, essentially. So let's just sort of do a simplified example here. Let's say that this average lake is 1 liter. It's a very small lake. 1 liter, then there would be 4.76 grams for every 1 liter of this lake. And Lake Parsons started out that way. So if this was 1 liter, then the concentration of salt would be 4.76 grams in this 1 liter. But then we evaporated a bunch of the liquid. We evaporated a bunch of the water. And as we evaporate the water, that's going to concentrate the salt in a smaller volume, right? So the amount of grams per liter is just going to be more because we have less water. We've got less of that solvent. So what we're asked to figure out is basically, how much did this go down to go from 4.76 grams per liter that it started at to 33.8 grams per liter, which is where it is now? So that's sort of the question. So there's a lot of different ways you can go about sort of solving this. The way that I'm going to set it up essentially is sort of this, I guess almost like a cross multiplication. But if we say that Lake Parsons started at 4.76 grams of water of salt for every 1 liter, what we want to figure out is how many liters is it going to sort of take to get to this 33.8 grams per liter. So I'm going to write 33.8 grams over 1 liter. So essentially what we're saying here is this 4.76 grams, we're going to say that was sort of our original state, right? So originally, if we had 4.76 grams per 1 liter, that's our 1 liter here, we're going to end up getting rid of some of that liquid, but I want to know how much liquid that's going to take to get to this 33.8 grams per liter. So if we set it up this way, let's go ahead and do the calculation. We can sort of show what we're talking about here. And we solve for x, so this is sort of a cross multiplication, solve for x situation. X liters is going to equal 0.141 liters. So let's talk about what this represents. This 0.141 liters represents the volume that would have to be over here to get to this concentration, right? So this volume that we have here is 0.141 liters. And that's going to be sort of what remains if we had originally 1 liter, right? So we had to make some assumptions in this case. Basically, we don't know how big the lake is, but if we take 1 liter from Lake Parsons, or we take 1 liter from the original solution, and then we evaporate it to get to that concentration of Lake Parsons, that's really what we're doing. This is the concentration, this is the volume that we would have to get to this concentration that we found in Lake Parsons. So now the question becomes, well, what is the percentage, so the percentage of Lake Parsons which has evaporated since it became isolated, that represents this distance here. So what did we start at here? Well, we started at 1 liter, right? We're sort of drawing this analogy from our average. So if this is our 1.00 liters, we decrease to 0.141 liters, we can, there's a number of ways to go about that, but basically what I would do is I would say, well, 1.00 liters minus 0.141 liters equals 0.859 liters. That's the amount that has dissolved, or excuse me, that's the amount that has evaporated. If I divide that by 1.00, multiply that by 100 to get a percentage, that's going to be 85.9% has evaporated. So, like I said, this is definitely a confusing, sort of problem-solving type of topic. But when we draw some pictures out and we sort of say, okay, well, what is it really asking? This picture here where we're starting, at this 1 liter, assuming that it started at 4.76 grams per liter, as we lose our solvent, as we lose our water, that's going to concentrate our solution. So what we solved for basically was, if we started at 4.76 grams per liter, how much volume would we have to convert that essentially to 33.8 grams per liter. So that's definitely the more confusing or challenging type of topic. I'm going to do one more that's a little bit more straightforward. Maybe I should have switched the order here. But this one is a little bit more straightforward. And once you maybe can do this one, you can apply what you've done with this one to the other example that I just did. Okay. So this one says a biochemist carefully measures the molarity of salt in 73 milliliters of this cell growth medium to be 40 millimolar. Unfortunately, a careless graduate student forgets to cover the container and some of the solvent evaporates. Okay, so let's go to, again, draw our picture. So we've got our growth container here. We've got originally 73 milliliters, and then the concentration here is 40 millimolar, and then we leave it uncovered, and I should have made these a little bit bigger. Our solvent level decreases, right? So we've decreased in our solvent, so we've concentrated our solution here. This is now 8.8 milliliters, and then we're asked to figure out, what is the concentration of this new solution. So essentially we've started at this case here, and then we're going to this case here where we're evaporating some of that solvent. So what we're looking for is, again, the concentration in millimolar, which is going to be the millimoles over the liters of solution, millimoles of salt over the liters of solution. And we know what the liters of solution is. We know that this solution over here is 8.8 milliliters or 0.0088 liters. So we know this bottom part, but what we don't know is this millimoles of salt yet. But we have a way that we can solve for that because we know what the original solution was made up of. So if I take 40 millimolar, and millimolar is, how should I write this out? Maybe I'll just write it down here. 40 millimoles over liters, right? That's what this millimolar represents. And I multiply that by 0.073 liters. So just converting this milliliters into liters, my units of liters will cancel, and I'll be left with 2.92 millimoles of salt. So this was the number, the millimoles of salt, the quantity of salt that was in this original solution. Now we've evaporated some of our solvent. We've gone to 8.8 milliliters. So if I want to find the concentration now, it would just be this 2.92 millimoles of salt divided by 0.0088 liters. So converting this 8.8 milliliters into liters. And that equals 332 millimolar. So millimoles per liter is millimolar. And now we would need to convert this to 2 sig figs. If I look at my numbers up here, we definitely have 2 sig figs. So this would be, if it were me teaching the course, I would be okay with 330 millimolar, but 3.3 times 10 to the second millimolar is a better answer. It's definitely not ambiguous at all how many sig figs should be in this number here. So this is definitely a better answer. So again, hopefully this makes sense. We're basically just decreasing our solvent, our solution volume, but our salt is not going anywhere. It's just being concentrated to a higher concentration. We should double check to make sure that this number is higher, right, than this 40 millimolar. If we are concentrating our solution, we should absolutely expect that we're going to be at a larger number here, a larger concentration. And obviously 330 is much more concentrated than 40. There are other ways to tackle this problem. You could actually do this somewhat like we did in the previous problem with that sort of cross multiplication type treatment. But I like this method as well to sort of show all of our units. So either way, hopefully that makes sense. And thanks for your time.